is called coin rotation paradox. And today let's see what's that. First, we have two same coins and let's rotate it. Right here, and let's see. Now it's one rotation, right? Let's see. Here. Okay, now it's two rotation. Here has no any tricks, or you can try it yourself. Now we cut the circumference and pull it to a horizon. You can think the coin is rotating on the horizon. Of course, it have one revolution because now the horizon is a curve. When the coin is rotating himself and the horizon is rotating. So how do we understand this hard problem? Now let's imagine this coin is not rotating himself. That means someone is pushing him, he's sliding its foot on the horizon all the time. But actually, the horizon is a curve, so the coin moves around like this. So that's why we want to know when the coin is rotating himself, how many revolutions, and you need to plus one revolution. Okay, now we change the rotating coin to a little bit small. Of course, the radius of this one over this one is 1 over 2. So let's see, because the circumference is 2 pi r, right? So if this one is 2 pi r, so this one should be 2 pi times 2r, right? Of course, so the circumference is 1 over 2, right? So of course, this one, how many rotation of this coin, how many revolution is it? It says 2 plus 1 revolution is like this. Of course, so we can have an equation, right? The radius is 1 over n, so it should be n plus 1. So, but if we say this one is a, the radius is a, and this radius is b, so of course that we can say b over a plus 1. This is a blob. This is a coin. The coin is sliding on the blob's surface. Sometimes it's clockwise and we call that is positive, and sometimes it's unclockwise, we call that is negative. But when it go back to the start point, it equals rotate 1 revolution. And let's see the coin rotating on a equilateral triangle. And let's see it, and the coin is first right here. The center of the coin is perpendicular to the vertex, and the vertex is on the side. The coin rotate right to here. In this period, the coin is like rotating on an horizon. And right here, now it's going to right here. It's perpendicular to the vertex again. And now what's happened? Right, rotating to here, and of course here is 120 degrees, and you go right here and rotate again and go and rotate again, and of course so that it should be the parameter. And what's the distance right here? Of course it should be the parameter of the triangle over the circumference of the circle and plus 1. Now let's see how to calculate how many revolutions actually. And let's see, this is a 1r and this is 3r. And now we need to calculate the distance of the circle center traveling. And let's see, the 1r, 3r, so this is 4r. And the parameter of the big circle, it should be, and the radius of the big circle is 4r, so it should be 2 pi times 4r, and it's 8 pi r, and 8 pi r means this distance parameter, and 8 pi r over the 2 pi r, and it's equal to 4 revolutions. Okay, actually this is true for any shapes. It means if it's triangle, square, pentagon, hexagon, and so on. Okay, now let's go back to see the triangle, and let's write it down. It should be the center. The center just means the distance of the center. Okay, the center, and the center, okay, is this one, and over the circumference of the small circle, and it's equal to the perimeter of the triangle. Okay, this and this. It's the perimeter of the triangle, and plus the circumference of the small circle, because it's this one, and this one of the circumference of the circle, and the over circumference of the circle, and that's equal to this over this is n revolution, we said that, and it's plus this over this is a 1 revolution. Now let's have a look. The small circle is rotating within the big circle. The small circle is rotating like this. Now let's imagine the small circle is not rotating. This point is sliding on the big circle with clockwise. This direction is inverse with its rotate direction. And now let's see. At first it is rotating on the horizon, and now the speed is decreased. Let's write down the equation. The distance of the circle center traveling and over the circumference of the small circle. And it's equal to the big circle, the circumference of the big circle, I just pointing in the middle. That means the big circle. And minus circumference of the big circle minus circumference of the small circle over circumference of the small circle. And it's equal to n is this over this, and minus 1. Let's play a game. If we only focus this rotating coin, so that means we can forget this coin, the other coin. And let's see. That means what you observing is this one is rotating 2 revolution. Here, back. And now let's play another game. If you're very tiny and you stand at the middle of this coin right here, and let's see. If you focus this coin, you will see here, and now you will see this coin has 1 revolution. Now let's play a game. This is a coin, and I am a coin too, and these 2 coins have the same radius and. You see, I have a half rotation, and I think I have 1 rotation. Right here. Okay, so you see I have 1 rotation, but I have 2 rotation. I think I have 2 rotation. Okay, now the 2 coin radius is 1 over 2. Okay, here I have 1 rotation. Okay, here I have 2 rotations. Okay, I'm back. I have 3 rotations actually, but you see 2 rotations. This is the sun and this is the earth. We stand right here and let's see. This is the sun and this is the earth. Here has an arrow and here has a man, and the man is faced to the sun. Here is noon, and we rotate right, maybe right here, and right here, respect on us, we'll see here is noon. But if you can see the alien or the stars observed, they will see a little bit back. Sorry, right here and a little bit back. Right here, they think it's a day. Of course, when the people see right here is the solar day, and the alien see right here is called the sidereal day. And we rotate. When you rotate right here, the people on the earth will see here's the noon again. But the alien or the stars observe middle night right here. So they lost a half day, and we rotate again. Rotate back right here. Now, everyone is noon. People on the earth is 365 days a year. That is called the solar year. And the aliens or the stars observed lost 1 day. So they need to pass 1 day. So they have 366 days a year. And that's called the sidereal year. use physics. And let's see. This is the coin, and this is a horizontal. Actually, you can imagine this is another coin. You can imagine that. Okay, and we can say we can imagine here's a hole, right? And we plug a stick in here, and we can push this stick into the rows, and you can get a velocity v1 right here. And because this one is a hole. This is a hole, so that means this point has a v1 speed, v1 velocity 2 right here. And this is the lowest point of the rotating coin. And let's see. Okay, don't forget, these two coins has a little bit touch, so they have a little bit of resistance. Resistance creates the velocity v2 right here. So these two velocity are balanced, and this point don't move, and this point is called the instantaneous center. and now let's see. And there's a little bit string here because we push the stick, right? We push the stick, so that means the coin need to go front. How can we go front? How can the coin go front? There's only one way. Is the coin is rotate. It's rotating. So now we need to change the model, and let's see because the coin is rotating. So that means that we have an angular velocity here. Okay, so and we times the radius, and we can get the linear velocity. And so in another hand, you can say the linear velocity. If we want to get a linear velocity, so that means you need an angular velocity. Okay. So now let's see. Now let's change our model, and let's see here. Let's see here. Okay. Let's see. This is a coin. This is a quick coin, rotating coin. And we can see we put a stick from the center, the circle center from the circle center here, from the circle center to this circle center. These two circle center, and we have a stick right here, and we push the stick. So we're rotating, and of course this point have a velocity v, and this point is saying we will have a velocity v, and this have a velocity v2. Sorry, it's a v1, and here I have a v2. And let's see, because this stick is rotating, right? Rotating, so stick rotating have omega 1. And you see, because this one the stick is rotating, so that means the coin is rotating like this. So it will have omega 2. Have omega 2, and then where come from the v1? The v1 is, and write it. The v1 is equal to the omega 1. The omega 1 times the 4. R because let's see because the 4R, because the stick is this one, and it's because this one 1R is 3R because the one that was 3 the radius. Okay, so it should be 4R, and it's v2. What is v2 equal to? It should be the omega 2, this one, and times R. It means 1R. I just write it R. And let's see, we can take this point speed because the tip point speed velocity. You can say that is the velocity of the instantaneous center speed of the velocity of the instantaneous center. So that we call this the VI, and this VI is equal to, because you see this one and this one, so we can say it's v2 minus v1 because they are balanced, right? So they minus and will equal to 0. And let's see this one, and we can put this one in here, this one in here, and let's calculate it. No, should be v1 minus v2. So it should be omega 1 times 4. Omega 2 times R is equal to 0. Okay, now let's see. You can take the R out right here, and you can take the R out, and you can take the R out, and both sides divide R because it is 0, so not changing. If you both sides divide R, then it's equal to out. Okay, so it's equal to, and you put the omega 2 right there. So actually that means the omega 1 over omega 2 is equal to 1 over 4. Okay, so what that means? Let's see. If we integral, because we are integral it, and what's time is the 0 to the t is the time, and it's the omega 1, and that is the omega 1 of t. Omega 1 in terms of the time, and it's equal to what? It's equal to pi, right? And here, because we said the stick rotates here because pi, right? And it's integral 0 to t is same as it's omega 2. And we got the omega 2 times t time. Okay, and it's equal to 4 pi, right? You can lay out as 4 pi. And so what that means, this pi is 4 pi. So that means when the stick rotates rotate pi to here, and you can imagine this small coin rotate 4 pi, rotate 4 pi, so that is rotate 2 revolutions. You can feel it intuitively. Let's see, because it's 4 pi, you can imagine this coin rotating is 4 times faster than the stick rotating. And you can imagine, if the coin is much more smaller, and you can see the radius is 1 over 6. So what's that happening? You can imagine. This is the coin rotating is 7 times faster than the stick.